now what we're going to do is we're going to start looking at the other side, and we're going to open circuit that side there. So we know that I1 must equal 0. So we get here Z22. Since I1 equals 0, A times I1 must also be 0. So there's no current coming through that current source. A current source of 0 looks like an open circuit, so that's just gone. All we have is R2. I can just immediately say that Z22 is R2. All right. Now Z12 here is equal to, let's just write it out, V1 over I2. Well, we know in that case, since there's no current there, that's just going to be open circuited. So whatever the voltage is here is going to be the voltage here, because there's no current through that resistor. So there's no voltage drop across the resistor. So whatever this dependent source is going to be your voltage. So V1 equals V times I2, because there's no current going through that resistor. So I can say immediately that V1 equals V times I2. Well, that's nice because I can sub that in and have an I2 over an I2 will cancel. So I can end up with Z12 just equals B. So there we go. We just found the four perimeters. Yeah.
Z21 is
Z21?
Yes, that's the matter.
Why would you think it'd be 0?
Because if you want to open the circuit, this second right-hand side,
Right.
both your dependent sources go to 0.
Not all my dependent sources go to 0. This dependent source is dependent on I1. Yeah. No problem. Okay, so I've got my Z matrix. ZEQ1 was what the problem called it. Anyways, it equals, let's put it in matrix form. R1, A, R2, R2. Hooray. Okay. Now the next part of the question, I believe, read, what's the equivalent Y matrix? So part B said, what's Y equivalent 1? Given this Z matrix, what's an equivalent Y matrix? That being Y is equal to the matrix inverse of Z. Oh, that's not actually the one. So remember that these guys are inverses of one another. So if I had Y, I would take the inverse to get Z. If I have Z, I would take the inverse to get Y. Anyways, this ends up being, this is where things got a little more complicated when I started working it out by hand. So let's say that this equals, remember to get the inverse of a matrix, you go 1 over the determinant times, and then for a 2 by 2, this one's a little simple formula. So let's do 1 over the determinant. The determinant is R1 times R2 minus AB R2. So we have R1 R2 minus AB R2. Or if you want, you can pull that R2 out the front. So I'd say R2, R1 minus AB times, and then we gotta have a matrix over here. So that matrix would be R2, R1, right? You just flip those ones around, and then you just stick negatives in front of these ones over here. Negative B, negative A, R2. So that would be Y equivalent. And then the same matrix down here. This is where things got a little hairy. So the next part of the question says, all right, given a two-port matrix that we found here, Y equivalent 1. So given that Y matrix over there, and then given a particular connection here, Y equivalent 1, what's the name of that connection? Uh-oh. All right, maybe we should take a moment to review our connections. Here's a cascaded connection. Cascaded looks like this. Okay, those are cascaded. And that's when we use A matrices, and we multiply A1 times A2 times A3 times A4. A series connection looks like this. That's what a series connection looks like. For that, Z equivalent equals Z1 plus Z2. Just remember that resistors in series, you add them, right? You add the resistances or impedances. And then the last one here is this kind of a connection here, which is called a parallel connection. So the question would say, what's the equivalent Y matrix? Y equivalent to, based on these connections, what's a two-port network that looks like those two? And remember, you add your Z's, you add your Y's as well. So what we can say is that Y equivalent 2 equals Y equivalent 1 plus Y equivalent 1. They're identical, just equals a scalar value of 2 times each one of those. That's a parallel connection. Use Y's for a parallel connection. And then if we wanted to, we could say, given that, what Z equivalent to? So now we have Y equivalent to. So what's a Z that looks just like that? We take the Y, Z equivalent to. Well, we can just say that Z equivalent to is equal to Y equivalent to inverse. And it actually ends up not too bad. It ends up being, I think, 1.5. Let me just check if I actually solve that. Anyways, I think that's probably where I'd want to stop this part of the question, because this is where Adam said, okay, this is going to take way too long to do. If we actually gave you numbers for those values, it probably wouldn't be too bad if we hadn't done that. So I'm going to skip ahead to sort of the last part where we have a loaded Z matrix, and we can actually come up with example values. We can come up with component values just to make our lives a little bit easier. So the key to solving these circuits, and bearing in mind that that was too complicated, so it's simpler than that. The key is just remembering how you go about shutting off a current and shutting off a voltage so you can analyze the circuit. It's always a good idea if you find that you're getting confused to actually draw out the circuit with either shorted or open. That will just organize your life and make it a little bit easier. Okay, so we're going to make up a Z matrix. I did it symbolically, so we just plug in numbers along the way here. So let's pretend we're going to put a load on here. So we'll have an input voltage, we'll have a source resistance, you have a Z matrix, and you have some particular load. And you have some output voltage here. So you got a V in and a V out. The question was something like, what's the voltage gain? And the voltage gain, of course, is always AV equals V out over V in. So here's how you solve one of these circuits. You're going to have your two equations that come from the two-port network, right?